Okay, good morning. Hello. Hopefully we can all hear me. I'm back in my normal location. So, welcome back to your favorite class. Yes. Okay. A couple of announcements. Number one is that your homework number 5, which is unbuckling, we do on Wednesday. And I realize I've been kind of aggressive with the homeworks and labs and exams lately, so I decided to take a break this week in lab. All right. So this week in lab, we're not going to have anything during the lab period, so you can take that time to work on homework or, you know, drink an adult beverage or something else. I don't know. Uh, do for those of you who are of age, um, or whatever, or work on something else. Okay. I feel like we've kind of been pushing a lot lately, so there you go. No actual meeting during the lab period this week. I will be around if you want to pop into the meeting and ask questions about, homework or whatever. Um, so that's that. Your lab will still be due at the beginning of the lab period on buckling. So make sure that you're doing the lab. Okay. Right. So that's that. Um, any questions on what we have going on? I think that's kind of the only announcements right now. Nice to see all of you back in person. So I'm back on Central Time. Means I got to wake up earlier. Dang it. All right. So let's get back into it then. And I sort of mentioned this before, but we're on the strain transformation notes. And I kind of just pick up where we left off. This is notes where we kind of left off talking about plane stress and plane strain. And I spent the whole lecture on plane stress, plane strain. Hopefully we're kind of like locked in now. But the idea is that plane stress element has no stress in the third direction. Plane strain element has no strain in the third direction. Know the differences between and how to calculate. Okay. I'll do something with plane stress and plane strain on your next homework so you can kind of clear it up. All right. Now I'll say moving forward, we're going to talk about strain transformations and principal strains in the next portion of the lecture. And principal strains and strain transformations have equations that look very similar to principal stresses and principal stress transformations. So there's full derivations for how to do this in the notes, but I'm not going to really beat it to death because we've already basically seen these equations except for with stress instead of with strain. So what I'm going to do is I'm just going to do a quick overview of what is strain and how does it maybe look in 3 dimensions, since this class is all about 3 dimensions. And then we'll just present the equations for strain transformations in 2D, which is kind of what we really need to focus on in this class. And we'll do principal strains in 2D as well. And that's pretty much going to be pretty much it. We'll do a couple of example problems and then we'll move on from strain transformations. Okay, so let's get into that now. We'll start in strain transformation notes, and I'm going to pick it up sort of where I left off. And we're going to talk just a review quickly on what is strain, both axial strain and shear strain. So review here. And we'll say strain at a point. All right. And so in your 2004 class, you should have talked at least somewhat about strain. And the first thing we can talk about is this one-dimensional axial strain. So you probably learned that if you had some long prismatic member, a bar or a rod or something like that, this was your original configuration. Let's say it has some length L. Original length, this is undeformed. And then you stress it somehow, you pull on it in sort of some axial direction, then you might get a deformed geometry. It sort of looks like this. Or it's sort of shrunken in that second direction. And it's extended here some amount, which I'll call delta N. All right, this additional amount that it's sort of like extended is delta N. So if we sort of say that this is the like X direction, then we can say that like the average strain, and what would be the X direction, is the change in the length of this bar, this is delta N, over the total length of the bar L. So this is sort of like an average axial strain over the whole length. okay? Now, if we're interested in strain at a point, that's different than maybe the average strain over the whole length of this bar, right? Maybe you have some weird stress state where like there's a high amount of strain in the middle and a low amount of strain on the edges, okay? And yes, you can calculate some average strain over this whole length L, but maybe the strain is different at various points along L. Could be the case, okay? So the idea here is if we want to talk about strain at a point, basically you want to take the limit of the expression above here, this guy, as the length goes to 0. So take limit of average as delta L goes to 0, right? As this like total length goes to 0. So the expression that you might see there is like, let's say you have some arbitrary point here on the bar. Let's call it point P. Then the strain generally at point P, I'll say sort of in this x direction, is the limit as this like value of L, let's just call it L, not delta L. Limit as L goes to 0 of this delta N on L. Or you might see this written as something like the change in delta N. So this is delta N, a little bit weird. Maybe we'll use the absolute derivative. So this is d delta N over dL. What is the change in this change in length? Sounds a little bit weird, but the change in the change of length per length. Okay, yeah, strange. But hopefully we sort of understand what I mean, is that like you have some original length of a bar and maybe it extends with strain. Think about that happening maybe at a point. You have one tiny little point, it's got some original length to it, maybe it's very, very small. And with the strain that's localized at that point, it extends some small length. Okay, so that's generally this equation. So this change in the length divided by the original differential length, right? So it's kind of like your 1D axial strain. So you could also consider about like a 2D state, which we might examine for shear strain. Okay, and so this is specifically at a point. So at some point you might represent a two-dimensional space with like a two-dimensional square element, which you've kind of come to know and love. So in 2D, at a point, you might have some small infinitesimal lengths of your pieces. So differential 2D element that, let's say, looks like this. Here, this is X, this is Y. I'm just putting a coordinate system on here. And you might have some dimensions to this element, which might be on the surface, which this might have a dimension of dy. Let's say that that length of that particular element in that direction is dy. And the length of the element in this direction is dx. So these are the undeformed lengths of the original pieces. So undeformed, it's dx by dy. Sort of makes sense. And let's say we apply a shear stress to this now so that it has some sort of elongated state. And I'm really going to exaggerate this here. Okay, so we'll say deforms. And I'll do this in red just so we can sort of clear this up. And I'll do my best to sort of draw this as cleanly as I can. It's got like this rhombus shape here. All right, something that looks like that. All right. So in this deformed condition, we put some shear on. So here's some shear on, not to be confused with the musical singer. We're putting some shear on here, like so. All right, this is going to cause pure shear deformation. So we don't have any axial deformation here. It's just this sort of like shear deformation. And let's call this like tau xy. So your definition of shear strain, which you sort of should have talked about, is the total angle. Well, let's define some additional things here. That this dimension here that has been formed, we typically will call little delta y. And this distance which is formed here we'll call little delta x. It's sort of the amount that these like edges rise up because of this like shearing strain that we're sort of like pinching on the edges to cause this particular form. All right. So this angle here is going to be something like the tangent of delta y on dx. And this here is actually half of the shear strain. This is gamma xy on 2. And that's because the other half comes from sort of the other side of the element, and that's here. So this guy here is like tangent of this displacement delta x over the original length, which was sort of this dy, okay? So that is this angle here as well, and this is gamma xy on 2. All right, so this shear strain here, gamma xy, can sort of be written in a combination of ways. But the idea here is we'll assume small angle. Assume small deformations such that tangent of whatever we have inside there is equal to just whatever that is. All right, we want to be a little bit more specific. Maybe we'll say tangent of, let's say, some arbitrary angle phi is some arbitrary angle phi. Then we can write our shear strain in a little bit clearer way. You'll say something like gamma xy on 2 is equal to, we're just kind of going to get rid of this tangent function because the tangent of a small angle is approximately equal to that angle. So this is either delta x on dy, or this is delta y on dx. All right. Since we have like conservation of angular momentum in general, we'll say that generally delta x and delta x equals delta y. And your original dimensions of this piece, dx, are dy. So we have a square piece, and when we put a pure shear strain on there, we're deforming equally in x and y directions by this pinching effect. All right, with that in mind, you sometimes might see this written as delta x over dy plus delta y over dx is the total shear strain. So that just kind of comes from sort of expanding this idea. Or if we sort of make some of the assumptions above, the same idea sort of holds. is that delta x over dy equal to delta y over dx. This is all sort of the same. I'm just repeating. And you might see this as, since the sort of denominator is the same, change in x plus change in y over the original dx. Same thing as these changes in lengths over dy. So these are a lot of different variations in how you might see shear strain represented. But I want to draw attention to particularly like this equation here, which I've sort of mentioned before. This is probably the most common definition that you'll see. Where it's just like looking at what is the change in sort of this little itty bitty length that we have divided by the original length of that element, right? So when we go through the strain transformation equations, which I'm just about to present here without derivation, you'll see that they look a lot like the stress transformation equations, except that there's like a factor of 2 that is different, specifically with the shear strain. This is where that factor of 2 comes from, here, okay? And it's this idea that when we define shear strain, we're usually looking at like 1/2 of the deformed rhombus element, okay, when we do our derivation. So I'll make this note here. That when we derive strain transformations in principal strains, we'll use gamma xy over 2 in the derivation. And you can sort of like dive into the notes if you really want to see sort of what that looks like. And so because of this, there's a factor of 2 that floats and looks different than the stress transformation equations. Okay. So the strain transformations have a factor of 2 difference in shear terms when comparing to stress transformations. Okay, keep that in mind, and when I write the strain transformation equations and principal strain equations, I'll point out exactly the differences in what I mean. Okay, so to sort of close out sort of the back end of what strain might look like, since we're kind of in the 3-dimensional world, let's try to look at what strains are in a 3-dimensional sense. All right. So this class is all about going from 2D to 3D. So let's draw an undeformed 3-dimensional element. And that would look something like this. And here I'll just make this an arbitrary space where this is like X, Y, Z. All right, this three-dimensional cube, we're saying it's like this differential three-dimensional element, and it has very small side lengths dx, dy, and dz. So here we're going to have something like dx, dy, and dz for these like original lengths. And obviously, if we have a cube, all of the angles that all of the edges make with each other are 90 degrees, right? So obviously 90 degrees, 90 degrees, and 90 degrees. I could draw them all, but you get the general idea is that all of these angles that are sort of incident on each other for this perfect original undeformed cube, 90 degrees. It's like the temperature of my heart. That means I'm cold-hearted. Okay, darn. I was trying to sound warm-hearted, but I'm not. I guess that's a bad thing. All right, so let's look at what happens if we just put an arbitrary deformation. And we're here going to include like axial and shear deformations. So you guys know I'm the best artist in North America, right? So here comes the best picture you've ever seen, except for one thing. It's not. But I'll do my best. All right, so let's say we have a new deformed picture. It might look something like this. Okay. All right, that's not half bad, actually. And the idea here is that the edges now might have changed length from just axial elongation, but also the angles at like the intersections of these lines have also changed. So let's sort of define these new deformed sort of dimensions on this new cube. So we might call this new length here dy prime. We might call this length here dx prime. And on the top surface, oh, sorry. Yeah, let's make it, this is dz. Sorry about that. And here we have dz prime. We also may have new angles. I'll call this angle here, which exists, theta x, y prime. It is now no longer 90 degrees because of the shear that we may have like incident on this particular guy. Maybe let's call this guy up here is going to be theta xz, theta prime xz. This angle that's sort of made in this xz plane. And then we also have a theta yz, which will sort of be here. Okay, so let's kind of consider or recall our definitions of the strain to sort of come up with a like axial and shear strain here in all three of our principal directions. Okay, so axial strains are going to be something like epsilon x is the change in length over the original length, which we kind of wrote before as something like this. So the change in length over the original length. Similar in y direction. and similar in the z direction. Like so. Our shear strain. I'll sort of beat to death kind of the shear strain XY because I think that's kind of the most easily visible. But remember, if we wanted to find, let's say, shear strain XY, it's a combination of, I'll sort of do my best to sort of make this clear. This angle here plus this angle here. So here is gamma XY on 2, and this is also gamma XY on 2. Right. Remember those stupid floating values of 2 I was talking about here? They kind of manifest and you sort of see them clearly. All right. So if I actually wanted to find what that gamma XY is, I want 90 degrees minus theta XY prime. That's the idea. So hopefully we can sort of see this. It's 90 degrees, or I'll work in radians to be a little bit more appropriate. This is going to be pi on 2 minus theta xy prime. That gives me sort of those leftover gamma xy on 2 halves. Hopefully we sort of see that. All right, same idea for gamma xz. It's pi on 2 minus theta xz prime. And gamma yz is going to be pi on 2 minus theta yz prime. All right. So I hope that this is like helpful as showing like these strains in 3 dimensions. You know, you sort of got this like cubic element that you can sort of like shear and pull on in all these different directions. Sort of like helps us just define and sort of see in 3 dimensions what's sort of happening. All right. So that's that. Now, like I said, I'm going to sort of skip over the full derivations here, and let's just jump to the strain transformation equations. And full derivation and notes, and we're going to be doing strain transformations. So let's motivate this a little bit. And you've already sort of seen this in your combined loading lab. And let's say that you have some element, x, y, and your undeformed condition obviously looks like this. In this like xy coordinate system. Now we apply some stresses, x, y, gamma x, tau xy, to sort of deform this guy. Now let's say that he shrinks a little bit, I don't know, by the stresses that we apply, and you've got something that might look like that. Who knows? Because you've got maybe some like negative sigma x going on here, maybe some negative sigma y going on here, and you got some shear strains going on here. Who knows? Okay. So that's like a deformed condition. So this is what this element would look like in XY coordinate system. So in XY, let's say that you have these things. Epsilon x, epsilon y, and gamma xy. And those would be like sort of the shrinking of this element and the pinching of this element, and yeah. But you want to know, let's say epsilon n, epsilon t, and gamma nt in a new coordinate system, which is the nt coordinate system. So we've sort of talked about this before, and you've seen this with stress transformations. So maybe you have a new coordinate system, if this was x, y. And now you have some, hey, blue, new coordinate system, n, t. In the nt coordinate system, you might have some original undeformed element that, again, looks like sort of this square piece. The question is, how is that undeformed element in NT going to look given the same sort of strains that we might have seen in the XY coordinate system? So then how does it look? Let's do green. In sort of this new orientation. Maybe because of how it's rotated, we like completely get rid of the compression in like the t direction. So maybe this new element might look rid of the strain. I don't know. Maybe the new deformed piece looks something like this, the shear strain. Maybe. Does it look like that in that sort of deformed condition? Maybe. Who knows? But you could go through a derivation where you like slice through the element and look at the strains in the various directions, a lot like what we did for stress transformations. Okay, this is what I'm sort of bypassing in this particular lecture. All right, so this is fully in the notes. If you want to go check it out, check it out. I'm not going to ask you about the derivation for strain transformations. Okay, I'm just going to ask you to apply it. Okay, so the following. So assuming you have epsilon x, epsilon y, gamma xy, and what would be the rotation angle to get to nt, which again is this variable theta. Then you'd have something that looks like this. Will look very familiar. Bam. There's your strain transformation equation. This looks a lot like your stress transformation equation, which, if you recall, is the following. Okay. It looks a lot like that, but the factor of 2 is different. This guy is the difference. And that's because when we do the derivation for strain transformations, we have this gamma over 2 that's floating around that I sort of talked about at the beginning of the lecture. Because all that nonsense. You may also see the double angle form of this. Which is the following. Okay. And again, this looks an awful lot like the stress transformation equation, except for that floating factor of 2. So that's to determine what the strain is in the n direction. In the t direction, axial strain. So you could get the strain in the t direction by adding 90 degrees to the value of theta and plugging into the epsilon n equation. Hopefully we sort of kind of gather that. I'll just put the double angle form here. So this would tell you what's the strain in the t direction. Yes, this minus sign is correct. This minus sign is correct. The last thing you might want is sort of the strain in the NT axes. And again, derivation similar to sort of the shear stress, and it's going to look very similar. It's gamma NT. But again, factor of 2 floating. So here, -2 times epsilon x minus epsilon y sine theta epsilon theta plus gamma xy times cosine squared theta minus sine squared theta. Or if you want double angle form, negative quantity epsilon x minus epsilon y times sine 2 theta plus gamma xy cosine 2 theta. All right. Those are your strain transformation equations. Give you a second. We'll do copy down an example problem and maybe dive in the example problem on Wednesday. But you can see how these look a lot like the stress transformation equations, okay? There's that weird factor of 2 difference. So if you're doing strain transformations or stress transformations, you need to be sure you're using the right sort of equations, okay? That pesky factor of 2 from the strain floats around there. Okay, let's look at an example problem. Give you a second. Anyone still writing this down? Looks like we're all Gucci. All right. So here's an example problem. We have some element in an XY coordinate system, and we know the strains in the XY coordinate system. I want to know what are the strains in the NT coordinate system using our transformation equations. Believe it or not, you did something like this already in your combined loading lab, even though you may not have necessarily known what you were doing. You did pretty much this exact same thing by using that matrix to transform the strains in your combined loading lab, lab number 1. Might have time to do this one. Goes pretty quickly. Okay, I'll bring the picture in and bring the pertinent information here. So here's your picture. We want to find epsilon n, epsilon t, and gamma nt, given epsilon x here is 800 microstrain. Epsilon y is negative 1000 microstrain. And gamma y here is negative 600 microstrain. All right, so we're going to use strain transformation equations. Okay, but first I actually want to show what this element looks like in the XY coordinate system, undeformed and deformed, right? Just so we get a general sense, and then equations on Wednesday. So for undeformed, we basically have a square of material. Maybe I'll blow that up a little bit. It looks like this. Okay, so this is my undeformed configuration. In the XY coordinate system, we're told that we've got some strain here that's resulting from some stress that we don't know. But we're told here that we have sort of a positive strain in X, a negative strain in Y, and a negative shear strain. All right. So a negative shear strain is going to kind of cause my element to sort of, how can I draw this? My angle is going to increase here. So my deformed condition will look something like this. My angle is going to increase. Because I'm going to have like a negative value here over a positive value. If we think about the inverse tangent of that angle, right? Negative over positive. Okay. I'm going to have elongation in X. So this is going to get somewhat longer in the X direction. And I'm going to have compression in Y. So that's kind of a strange thing to draw. But let me see if I can do my best here. Again, we're going to have that elongation here. It's going to become more squat in Y, and it's going to elongate in X. This is a bit tricky to actually draw. My best to do it like this. Yeah, this is a strange one to draw. Getting more stout in Y. Yeah, okay. Elongating in X. So maybe something like this. This is like a huge exaggeration, but we get the idea. Strange one. And I really sort of exaggerated the compression in Y. But hopefully we get the idea. So here's like my shear angle, which is this negative angle. So that's kind of good to see. We've got the squat compression in Y, which is negative 1000 microstrain. And then I sort of tried to draw elongation in X here. Maybe I could have done a little bit better job elongating this a little bit more. But hopefully we saw that it sort of did elongate in that X direction. All right, so we'll compare that to what this might look like actually when we investigate a normal square of material in the NT coordinate system and what that might look like in the deformed configuration after we calculate our strain transformation. So we'll do that on Wednesday, and we'll break for now.